Welcome back. We have just a few word problems. They are not near as crazy as the ones I put on the midterm. These are pretty standard. All right, so the first two are dealing with Pythagorean theorem, because Pythagorean theorem often produces a quadratic, depending on how you write the problem. And solving that quadratic, you can then figure out some answer in the problem. The first thing you have to do is figure out where the triangle is they're even talking about. All right, so here, a 15-foot ladder is leaning against a house. Now that ladder can lean a number of different ways, but we need to, ground, you know what, green is a ground color. House. There, door, house. Yes, I know it's a horrible house. I don't care, it's my house. And then we have a ladder. It's leaning against the house. It's resting at a point that is 3 feet more than the distance from the base of the ladder to the house. All right, so base of the ladder to the house. So the base, usually the one on the bottom, to the house. Because the other part of the ladder is on the house, so its distance to the house is 0. The other end has a distance to the house. And then where the ladder is resting, here, sorry, forgot to cover the microphone. All right. So the ladder is resting at a point that is 3 feet more than the distance from the base of the ladder to the house. So I believe, and I should have been a little more explicit, though I think I copied this from the book, but the ladder is resting at a point a certain distance up, and that distance is 3 feet more than the horizontal distance. All right, so houses in math land always meet in a right angle. So we have a very weird looking blue, green, pink right triangle. So I'm going to kind of pull that out. There's our green. There is our blue. And there is the pink. All right. And then the question asks, how far away from the house is the ladder? That is our distance from the base of the ladder. So it's not asking you to like average or do any weird thing. So if that is what they're asking for, then that is what I would prefer to call X. So that way when I solve for X, that's the answer I want. Now in other problems that may not work, it may be more beneficial to make something else X. So sometimes what I'll do is I'll put a little star to be like, that's the thing I want in the end. Now it says the blue is 3 feet more than the green. So if the green is X, the blue must be X plus 3. Then the only other piece they told us is, snuck in at the very beginning, is how long the ladder is. 15 feet. All right. So we have 3 sides of a right triangle, and 3 sides of a right triangle meet or can be related using the Pythagorean theorem. So that's what we're going to do. A squared plus b squared equals c squared, where c is the hypotenuse, and the hypotenuse is always across from the right angle. So that's what we're going to use and solve here, and that will give us a weird looking quadratic. And we'll see how it goes. A squared plus b squared equals c squared. So which one's A and which one's B really doesn't matter. So I'll just go with x squared plus x plus 3 squared equals 15 squared. It does matter which one's the hypotenuse. So it's got to be equal to 15 squared. You can't have the x squared or the x plus 3 squared over there. All right. Now the only variable I see is x. This is an equation. It can be solved. So x squared is x squared. X plus 3 squared. And we've been doing our complete the squares, so hopefully this is a little more familiar now. We have x squared, double the 3 is 6x, square the 3 is 9. And 15 squared over here is the whopping 225. This is a quadratic. So we're going to combine like terms, move stuff over so it's equal to 0. So we have 2x squared plus 6x minus 216 equals 0. Now I could plug those three numbers into the quadratic formula, but wait. What do you notice about those three numbers? They're all even. So why don't we go ahead and reduce now so we don't have to reduce more later? Everybody is going to get divided by 2. So we now have x squared plus 3x minus 108. Now this might factor. In fact, I'm near positive it does, but let's go ahead and use the quadratic formula since that's what we're doing. So x is going to equal -3 plus or minus the big square root of 3 squared minus 4 times 1 times -108. So that inside will be a real number. All over to A. Told you. Every time. All right, let's crunch those disgusting inside numbers. Because once it generally gets past 100, my brain is like, I don't want to do it by hand anymore. So that is going to be 9 plus whatever 4 times 108 is. So we have 441. Now, if you're comfy with your calculator, you don't have to write this in between step, but I like to have whatever the number in the square root is written down before I start trying to simplify it. And in this case, oops, 441 to the 0.5 power would square root it, and it is 21. So we have -3 plus 21 all over 2 and -3 minus 21 all over 2. So the minus would give us a -24 over 2, -12. So that's weird. And then plus 21 minus 3 is 18. 18 divided by 2 is 9. So anytime I do a word problem, I rewind at the end. What was the question asking? How far away from the house is the ladder? That green distance, which I called x. Does it make sense to say x is -12 feet? In math land, we don't talk about negative distance. That's a physics thing. They use the negative to imply a direction. We do kind of talk about that in pre-cal actually, but not in college algebra. So the 9, the positive number, is our answer. But if I put 9 here, 9 plus 3 is 12. So that's why -12 is a result here, because -12 plus 3 would be -9. -9 squared plus -12 squared would equal 15 squared. So that's why we're getting that as the other solution. But 9 is the solution that makes sense in a real world sense. And we need units. So that letter is 9 feet away. And if you're actually familiar with your Pythagorean triples, the numbers that actually, there's certain sets of numbers that work in the Pythagorean theorem perfectly, and 3, 4, 5 is the smallest one. But if you take all three sides and multiply them by the same thing, in this case, 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15, you get a 9, 12, 15 triangle. All right, so there's that one. And the next one, it's actually not Pythagorean theorem, it deals with area. So we have a triangle. In a triangle, the height is 2 feet less than the base. So let's just translate that sentence before we even start drawing a picture. Height, H, is equals 2 feet less. So if I say 2 feet less than 10 feet, I would get 8 feet. So it is the thing minus 2. And in this case, the thing is the base. So it is going to be whatever the base is minus 2. All right. So I now have a mathematical equation that relates the height and the base. Cool. The area is 50 feet squared. Ooh. Approximate the base and height to the nearest tenth of a foot. All right. Now you might be thinking, well, how do I know what kind of triangle this is? Like, where's the base? Where's the height? So it turns out with triangles, as long as the base and the height meet in a 90-degree angle, it doesn't matter where they are. They don't have to be sides of the triangle. As long as those sides are equal, the area will be equal. Now, the angles it makes won't be. So for trig, we're a little more particular about how we define triangles. But if all you're talking about is area, it doesn't matter whether it's a right triangle or an isosceles triangle, because that height number would be floating in the middle for any of the weird triangles. So it could be like that, say, and that is totally fine. There's our height, and there's our base. Now, if I made it a right triangle, then the height would shift over, and then we'd just have a hypotenuse, be meeting in a right angle, but the area would stay the same because I'm just taking the height and just shifting it. I'm not stretching it or shrinking it. So our area formula would still preserve it. It's actually kind of fun to prove that. You can make a rectangle the same size as base times height, and then you draw the triangle on it, the weird one, and then you cut it, and you can actually take those cut pieces and flip them over and show that it's the same as these. Yeah, I know you didn't need to know that. All right, so area. What is our area formula for a triangle? And I just kind of like said it in talking about my weird example. It's the same as it would be for the rectangle, but divided by 2. Base times height divided by 2. All right. But we know the area itself is 50 feet squared. So instead of the big A, I can put 50. 1/2. And then I have B and H, but up here I said H is the same as B minus 2. So I have B times B minus 2. And that will be a quadratic that we can solve. And the answers will probably be a little uglier since they gave us rounding directions. Not always the case, but most of the time, if they give you rounding directions, it's not going to be pretty. All right. I don't want to deal with that fraction, and right now it's a fraction times the rest of it. So if I get rid of that right now by multiplying both sides by 2, I have 100 over here now, which I like more than 50. And then here, this is 1/2 times B minus 2. Do not distribute across multiplication. So 2 times 1/2 times B is the same as 1/2 times 2 times B, 1/2 times B times 2. I could rearrange those however I want. I could even mix in the B minus 2 and rearrange it as long as it stays the thing B minus 2. So what we're going to do is reassociate, and 2 times 1/2 is 1. They cancel out. And then we just have b times b minus 2, which is now b squared minus 2b. And we're going to throw that 100 over there. And now we have an equation to work the quadratic formula on. In fact, I don't think there's a pair of numbers that multiply to 100 that have a difference of 2. So, yeah, pretty sure we are indeed going to get ugly numbers. So negative b is negative negative 2 plus or minus the square root of b squared minus 4ac all over 2a. So this is 2 plus or minus. So that would be 404. The square root of 404, and then we divide that sum or difference by 2. Because they asked for a decimal, don't even worry about simplifying the 404. We could. We don't have to. As long as we're using our calculator correctly, why do the unnecessary step? They only asked for the decimal, so I don't care about simplifying it. So we need to figure out what 2 plus the square root of 404, oh look, that's a positive number, equals 22.099 divided by 2 is 11.0498, blah, blah, blah. So that is the plus answer. Now let's do the minus answer. 2 minus the square root of 404. And that is now negative 18.099 divided by 2, negative 9.049. Now they did say to the nearest tenth of a foot. So that is actually just going to stay 0.0. So we have 11 or negative 9 as potential answers here. Does negative 9 for a base make sense? How do you measure negative 9 feet? You don't. Distance lengths are, in math at least, we take the absolute value of them. So you might say you can measure a negative distance if you measure the opposite direction, but that is implying a direction. We very rarely, if we're going to talk about direction, it's going to say it in the problem. So we chuck out the negative answer. So our base here has to be 11.0. And the area was feet squared, so this is feet. So it's got an 11-foot base. And then take it back to the height is 2 less than the base. So if the base is 11, 11 minus 2, our height is 9.0 feet. Now normally that would actually round, but so 11 times 9 is 99, divided by 2 is 49.5, which is pretty close to 50. Now if you look, this was really close to 9.1 and 11.1, but that's just the way the rounding fell. I personally would like to see 11.0 and 9.0, because that's basically where the significant figures are, if you will, but not that mathematicians talk about significant figures. All right. Now, the third thing we have is very, very, very physics. In fact, this is the equation that will determine the time it takes your math textbook to hit the ground after you kick it off a building. Now, you know, normally they're like, oh, it's a ball, or oh, it's a frozen pumpkin. I like kicking math textbooks. So you standing on a building that has an initial height. You chuck it off at a particular speed, and it goes up, kind of pauses and then goes down and hits the ground. So this particular formula or equation will predict the arc that the math textbook would take, and what we are doing when we have the building, we have that as our initial distance. See, it says initial vertical position. That means the vertical position at time equals 0. So that means down here, if I'm calling the ground 0, then that's actually superimposing an XY plane. And then this is part of a parabola, and the intercept is the point at which it hits the ground. And that is what we have been solving in all of these, is find the intercept, find the solution, find when it equals 0. And in this case, this is our 0 line. The S for distance or height is 0 here. And this is the time equals 0 vertical line. Now, we don't know if it's going to be a like wide arc or if it's going to be a little short, tiny arc. I just usually draw it a little wider so it's better for the picture, because short and tiny like that's hard to see. So we're not asking how far away from the building. We're going to talk about what's the time it takes to land. Because either of these, regardless of the angle, as long as my velocity for the vertical part of it is consistent, they will all land at the same time. So our formula S equals -1/2 gt squared plus v sub 0 t plus s sub 0. G is the acceleration due to gravity. There are two different numbers. 32 feet per second squared or 9.8 meters per second squared. So the problem will either give you feet or meters, and then you must use the appropriate number. And then the time will then be in seconds because these are written in seconds. V sub 0 is the initial velocity, and in a math problem, we will just tell you that number and you just put it in. In physics, they usually start talking about the angle you put the object, which is going to change like how much of the velocity actually translates into the vertical versus the horizontal, and you start using pre-cal to do that. But at the base of it, this is still the equation that's going to generate how long till it hits the ground. And then S sub 0 is if it doesn't start on the ground. Like normally in physics, it's you kick the football, because that starts on the ground and then it hits the ground. So normally in those, your S sub 0 is 0, but instead, if it's off the top of a building, then you have an H sub 0 that's bigger. All right. Or S sub 0, sorry. So there's an example there if you want, but I'm just going to roll down to our example here. So we have a fireworks mortar is launched straight upward from a pool deck 2 meters off the ground at an initial velocity of 40 meters per second. So this is actually a really good example because theoretically a mortar goes straight up and explodes. If it didn't explode, then it would come straight back down. Now, the reality is they almost always have a tiny bit of a tilt when they finally exit the tube because of their shape. Or if you put a small mortar in a large tube, it spirals and then it doesn't go up near as high as it's supposed to. Yes, I'm speaking from experience. My ex was a firebug. Still is. All right. So the first question is just write a model to express the height of the mortar in meters above the ground. So they told us the pool deck is 2 meters off the ground. I mean, technically there's another like 1/10 of a meter or so for the, no, because the mortar starts at the bottom of the tube. So it's starting even with the pool deck. That's how we think about it. So that 2 meters is going to be our S sub 0. They straight up tell us the initial velocity of 40. So that's going to go for our V sub 0. And then the last one is we just have to pick the correct gravity. Since these are meters, we are going to use a gravity of 9.8 meters per second squared. So if I take meters per second squared and I multiply it by times squared, I end up multiplying it by seconds squared, so I just have a meters number. Then the velocity times the time. Meters per second times seconds would just give me meters. And then the height itself is in meters. In physics, if you pay attention to your units, a lot of times you can actually at least double check if what you're doing makes sense. Because if your units don't work out, then you couldn't do the thing you just tried. Or the calculation you just tried, I should say. All right, so let's go ahead and fill this out. Since that's all they're asking. S equals, we have negative 1/2 of 9.8 t squared plus the initial velocity is 40 with a t plus, and it's 2 meters above the ground, where we assume ground level means 0 height, 0 distance. And then just want to clean it up a little. So negative 1/2 times 9.8 is going to be negative 4.9. Now, in some of your more advanced physics classes or chemistry, the 9.8, it's actually a longer decimal, and your calculator may have that programmed in. For the purposes of math, just use 9.8. I know the other number would be more exact, but mathematicians are weird. Now in calculus, if you're doing like crazy calculus, but it's actually modeling real world stuff, yeah, go ahead and use the more exact, but you know, then you're in calculus. All right, so there's what number 1 asked for. Write a model, there's a model. Find the times at which the mortar is a height of 60 meters. Round to 1 decimal place. All right, so they are telling us the height is 60. Well, which of these things represented height? I know the 2 was 2 meters off the ground, but that's just the initial height. The whole function itself is height. So if they're saying, find the time when the height is 60, then we literally want to put 60 in place of the height, which is s in this case, I know. So we are going to solve 60 equals negative 4.9 t squared plus 40t plus 2. Now we could multiply to clear the decimal, but since this is a terminating decimal, it's just 4.9, not with any crazy other numbers. I would leave it like this and just plug the decimal into the quadratic formula, because like fractions look weird. Decimals, meh. Calculator will handle it. Because all we want here is the answers, the times that would be at 60. So to solve this, we're going to throw the 60 over. And then the numbers we are going to plug into the quadratic formula. So it is negative 4.9. Now I get pretty lazy, so I'm actually going to show you what happens if you use a negative a. Like after a while, I'm just like, when you do a lot of particularly these in physics, you will do so many of these. You'll get very tired of it. And you do some stuff with trig. Now, another thing you can do though, your graphing calculator can actually graph the height that we wrote here. Just put it in terms of x. And it'll show you a nice little arc. Whoop. And then on a second y, you could actually type 60 in, or you could type the resulting equation we have here. If you type the 60 in, then you're going to look for the intersection point between the y equals 60 horizontal line and the graph, and the arc you're going to see is going to cross it twice. If you use the negative 58 instead, then the entire graph, you minus 60, so you moved it down 60. So now the intercepts are going to be the points where it's 60 meters in the air, because we shifted the whole graph and dragged it down. So this new quadratic here, the solutions of it will answer our question, even though they are not the roots of the original height function. So there's our A, B, and C for the calculator. But like I said, you can con the calculator into just producing the answers, and here we just want the decimals. So cool. So t equals negative 40 plus or minus the square root of 40 squared minus 4 AC all over 2A. It'll still work. We just have to be careful about our signs. So that is a negative 40 up there. Plus or minus. The bottom is back to a negative 9.8. And then inside that disgusting square root. Now I'm not going to write, I could write the square root number, but I'm going to write what's inside it first because that will at least be terminating. So 40 squared is 1600. Now a negative times a negative is positive, but times another negative is going to be negative. So I'm going to put minus, and then I have 4 times 4.9 times 58. I got a negative number, that's why I'm pausing. All right. 4 times 4.9 times 58. 1136.8. Okay, my subtraction didn't work right. I'm using my phone. It doesn't always do order of operations correctly. So we get 463.2. That's the number under the square root. All right. So what we need to do is the 9.8 is negative. So our normal gut check for if I do negative 40 plus this square root, I'm going to get a positive number. You will. And then you'll divide it by a negative number, and you get a negative number. And you won't actually get a positive number because 463 is less than 1600, which is what 40 squared is. So even the plus side is going to turn into a negative number divided by a negative number. We're going to get two positives, which we should, because it should be as it goes up, it hits 60, and then if we pretend it was a dud, it would come back down and hit 60. So this is where I will very often I'm just gonna crunch it in. So a negative 40 plus the square root of 463.2 negative 18.477 divided by negative 9.8 1.8855 blah blah blah, one decimal place. So I'm just going to write 1.88 for the time. Now we're going to do the minus side. Everything's minus, so it actually all would be positive, but I prefer to type what I see. So negative 40 minus the square root of 463.2 negative 61.522 divided by negative 9.8 6.2777. I don't know why I'm reading it like Captain Kirk. I just felt it was the way to go. All right. Two different answers, but they are positive. They both have meanings for the problem. Now, what are the units? What do these numbers represent? So back to the beginning, we wrote t. Rewind more. The initial velocity was in meters per second. So t numbers are seconds. So then this is 1.9. That's what it would round to. 1.9 seconds and 6.3 seconds. So with 1.9 and 6.3 seconds, those are the two times. That's why they put the S in parentheses. So one going up and the other coming down. All right. It's pretty high in the air still. This must have actually gone pretty high. All right. Now it's asking, find the time at which the mortar is at a height of 100 meters. Same song, second verse. You might be thinking, why did they make us do the same thing twice? Exactly. So let's see what's weird here. So now it's going to be 100 equals negative 4.9 t squared plus 40t plus 2. Move the 100 over, and now it is a negative 98 going in that. Sorry. All right. So let's start writing it in, crunching it, and see what we're going to get. So t equals negative 40 plus or minus the square root of 40 squared minus 4 times the negative 4.9. Ooh, it's positive, but then negative 98 turns it negative again. All over 2a. Now, whether I change the sign or not, what is inside the square root will be the same. Because if I changed the sign, the b would then be the opposite, negative, but it squares back to a positive. And then the a and the c would both be positive, but then the full product would be a negative. So it works out either way. So 40 squared minus 4. Hold on, let's see if I can. 4 times 4.9 times 98. Why are you doing that? All right, fine. 4 times 4.9 times, well, negative 98. That is, so it's going to be minus 1900. 40 squared is only 1600. So we actually have negative 320.8. That is what's inside the square root. Can I square root this and get a real answer for my real world problem? No. So then it begs the question, what's this mean? So my t number makes no sense. I'm going to get an I. So this is not real. No solution. Or no real solution. All right, now let's think back. What were we even asked? The height, find the time at which the mortar is at a height of 100. I didn't get a time. So there must not be a time where this mortar would be at 100 meters. So it must mean it never actually gets there. That's what getting a complex I number means in the context of this problem. And if you actually took a look at the graph of the function, and if you graphed y equals 100, you're going to see it's above the peak of the graph. So it would look like, whoop, and then 100 would be somewhere above it where they don't touch it all. Whereas 60 is somewhere in there. All right. So that is our last crazy word problem. And that concludes our videos for this week. So 4 videos, yay. Again, I'm available in office hours and during class times. Please come and ask me any questions you would like. I'm literally sitting there waiting for somebody to ask me a question. It's kind of boring. All right, bye.